so today, here's what we're going to do. We're going to do the second day on 3-1, which is a combination of things that we have done before. So the combination of things we've done before is we have done linear regression. We were able to find the line of best fit on the last test. Most people were able to do that. Minor issues, not using the right one for 0, that kind of stuff, but you were able to do that. But now what we're going to do today, just so everybody knows to kind of stick with me and not try to get ahead, is we're going to have the calculator store that line for us so that we're not doing any rounding. The calculator is putting that line perfectly into y equals so that we can find the intersection of the two lines perfectly without having to do anything other than know how to use the graphing calculator. So we have a problem here, and it looks like this. And it says the population down here, the table shows the populations of New York City and Los Angeles metropolitan regions from the census reports for 1950 through 2000. Assuming these linear trends continue, when will the populations of these regions be equal? And I realized this is what we did on Friday. We're trying to see if here's the first line, here's the second line, where do they fit? But we don't get the equations for the lines. We get all of this. And so what we have to do is transfer this into the calculator and let Blinky tell us where these things hit. So we're going to start back here. And it says enter all the numbers as millions rounded to the nearest 100,000. Yeah, well, I agree with that because it's going to save us a little bit of time on putting the numbers in, but we'll lose a little accuracy when we do that. So it says step 1 will be to enter that data into our lists. Now we've done that before. We're going to use list 1 as the number of years since 1950. So that's important when we go to punch this in. And list 2 and list 3, we're going to use those rounded numbers. So let's first write all over our chart so we don't accidentally put something in wrong. Well, we're not going to put 1950 in as list 1. We're going to put a 0 in for 1950. And then 10 years later is 1960. And I'm just kind of scanning those numbers to make sure that they just keep going up by 10 every time. I don't want to make a mistake because I didn't read the values in the table. So there's another 10, so we should be able to just use 0, 10, 20, 30, 40, and 50. And then they said, don't punch the whole thing in. We've got New York City here, but just do 12.9 and think of that in millions. But with the next one, if we do that, we're actually going to have to round that to 14.8. But I think if we just put the decimals in here, I think we can remember to round as we go through that. In fact, we'll write ourselves a little message, round, right here. So that we make sure we get that. So list 1 is just going to be 0, 10, 20, 30, 40, 50. List 2, we'll start putting in those millions for New York City. And list 3, we'll put in Los Angeles. So I've got to get this monster rolling. That's not good that it's blank. Let's see if it's going to work this morning. Okay, you guys can go ahead and start punching in, and I'm going to load this back up again because something bad happened. And the whole reason I had this, there we go, had this running was because the person that's gone wants to see how we punch this into the calculator. All right, so stats edit. Through 50, everybody? Is that what we did for list 1? Okay, so now we are going to do list 2, and that's in those rounded millions. So we'll have 12.9. Then we'll have 14.8. 8, 16.2, 16.1, 18.1, and 21.2. Okay, so everybody take a second, double check we've got the same numbers in for list 2. List 3, we have about 4.4, 6.7, 7.0, which will, the calculator is just going to kick it out to 7, 11.5, 14.5, and 16.4. Now that one, when I look at the list, I think right away, well, maybe I punched something in wrong. But remember, these numbers in list 2, those all rounded nicely with everything in that tens of millions digit. And then list 3, no, it was kind of all over the place. You know, we don't have any control over the data. That's what it was. But what I do make sure of is that I have the exact same length of the list in each one of those rows. So now what I want to do is I want to have the calculator do that linear regression for me, but I also want it to store it where I need it to be stored. So don't try to go ahead at this point, go exactly at the same rate that I'm going at. So we're going to hit stats, and then we're going to hit to the right, calculate. And we see number 4, just like we've seen it before, there's linear regression. But now I have to be careful about which of the 2 lists I use. So I'm definitely using list 1, but if I'm going to do the New York data, I need to use list 2. So I'm going to have to change that by punching in second list 2. Some of you don't have to change a doggone thing. Everything is exactly right now. And now I'm going to skip frequency list, couldn't care less about that. But notice this is built to store stuff for us. It says store regression equation. So we just have to tell it to put it in y sub 1. We want it there. Now how we're going to do that is this little button over here by the clear key that says VARS. That stands for variables. Emmanuel, are you with us? Variables. And we look up here and we realize, well, we want y variables. That's where we want to put it. So I'm going to arrow to the right just once to get the y variables. And we are graphing functions, so we're going to pick number 1. And look at that. We get this really nice list of all the y values that we have when we graph. So we're just going to pick number 1. And now if we go down to calculate, not only is it going to give us that line of best fit, but we don't have to write it down. It already stored it for us as well. And it's a pretty good line of best fit with an R value of 0.96. It's not too bad. But go ahead and hit y equals. Look at that. It didn't round. It's perfect in there. It's exactly like it said it was for linear regression earlier. So there's the first line, all stored and ready to go. Anybody need some help right now because things are not looking the way they're supposed to be looking? So you have to do list 1, list 2, variables, all variables. You have to be really specific. Good work. Faith, you got some issues over there too? List 1, list 2. Variables, variables, functions. Now it should be good. Anybody else with something weird happening? right, so that was just New York. Now we have to get a line in there for Los Angeles. That means we don't want to use list 2 anymore. We want to use list 1 and list 3. So we're going to go back to stats. And we're going to do calculate again. So arrowing to the right once. Number 4 again. But now this time we want list 1 and list 3. So we're going to go down to that Y list and we're going to change that by hitting second number 3. So that'll become list 3. List 2 had the New York stuff in it. List 3 has the Los Angeles stuff in it. And we don't want to use Y1 because we want them both on there at the same time. This time we'll choose Y sub 2. So variables, Y variables, up the top to the right once, and then number 1 functions, but make sure you pick number 2 this time, Y sub 2. And then go down to calculate and press enter. So do it one more time. Stats, calculate, number 4, list 1, second, number 3, list 3, store required, variables, Y variables, number 1 functions, but number 2, Y sub 2. Oh, is that what yours did? Okay. So we have to do list 1, comma, list 3. Yeah, it's just a, that's it. Right before you do anything with a different variable. Okay. Everybody set? All right, so here's what we need to see. We need to see where these 2 lines intersect, because that's going to tell us when they were the same. So to do that, our window is not going to be negative 10 to 10. So let's hit window, which is this button right up here. And so far, we had the years 0 through 50, but it looks like it's going to take more than that. So 0 to 100 is not a bad idea. It might take 100 years for us to see those 2 as the same. And then Y min and Y max, well, that's going to be the numbers we put in the table. And let's see, our lowest one was 4.3, and our highest one was 21.2, but they didn't meet yet. So maybe if we do 0 to 50, we'll be able to see where that intersection takes place, because they're going to get bigger. I mean, the populations of New York and Los Angeles are getting bigger. So now let's hit graph. And hopefully we'll see 2 lines, and we'll see 2 lines intersect. There's New York. There's Los Angeles. They're definitely hitting. Do you remember how to get Blinky to find that for us? What do you hit? Second trace. Number 5. Bing, bang, boom. And there's Blinky. Blinky says, you know what, it's going to take 86.8 years, so about 87 years. So approximately 87 years from now. And it's going to be 25.6 million. Now, this is a word problem. So that means we don't want to write this as an ordered pair. We want to kind of explain it. It's called interpreting. So we know this thing started in 1950, and Blinky told us it's going to take about another 87 years in order to get this to happen. So we can take 1950 plus 87, and we can tell people this is the year when we're predicting this is going to happen. So let's see. Sometime in 2037. So we would put in approximately 2037. 2037, they will both be 25,600,000. Now, as we talked about last week, this is extrapolation. We don't know. You know, we don't know if they're going to keep growing the way they've been growing from 1950 to 2000. We don't have any idea. You know, might be an earthquake. California might just drop right into the ocean. There won't be any people out there. We don't know that. But we're saying if the trends stayed exactly like they are, then sometime during 2037, both of those should be about 25,600,000. So that was our practice for this one. We want to make sure we can get both of these lines hitting each other. So now what we have to do is go back and go through the process again, but we're talking about San Diego and Detroit this time. So we're not going to put in 1950, 1960. We're going to stick with what we were doing. But I want this one to be a little more accurate. So I'm not going to round any of the numbers for San Diego and Detroit this time. I'm going to put them in just as they are up there in the chart. So do you remember where we're going to put them? Lists. Okay, how do we get to the lists? Stats. Edit. Are we still using 0 through 50? Ooh, at least we don't have to change that, huh? But we have to go back in here, and we're going to put in the numbers as we see them. So San Diego was 334,387. Then we've got 573,224. 696,769. 875,538. 1,110,549. 1,223,400. Hey, my calculator goofed up. It didn't punch in all that stuff I put in for those last two. What's it doing? Do you recognize that? That's scientific notation. Yeah, it's using scientific notation because it says the numbers have gotten so large here that to store them, I'm just going to go ahead and use scientific notation. But we know we punched it in. So Detroit, 1,849,568. And yeah, you guys are probably done. Like I told you, this thing's a monster. 1,670,000. 144. 1,511,000. 482. 1,203,000. 339. 1,027,000. 974. And 951,270. Phew. All right, they're in there. So now, what did we do last time? We'll find out where did we go? Stats. Stats what? Calculate. Number 4. Change it to list 2. How do we get it? Variables, vars, y variables, number 1, number 1. down to calculate. Pretty good line of best fit, right? 0.99574, yeah, good line of best fit. How do we get the other one? That was San Diego. How do we get Detroit? Oh. Variables. Y variables. Yep. And number one again. Yep. Yep. All right, let's get the other line. Whoops. Uh-oh, more hands just popped up. So you got it all in there? All right. So let's get the other line. And that's going to be stats, calculate, number 4. But we have to make sure we're using list 3 this time. And that we don't put this in y sub 1, we want it in y sub 2. So variables, y variables, number 1, number 2. All right, our lines are in there. Our window is set from the other word problem we did, so we might be able to see what we need by just hitting graph.
She broke. She go.
I have no idea. What way to change like the numbers, like the
Yeah, we're going to have to change the window. It did not like that at all. So let's go into window. Now, here's the reason why. What's happening to the population in Detroit, everybody?
going down.
Why? The car business is done for. Yeah, the car business is done. So actually in the table, we might even see this from 0 to 50 years. And we didn't round, so we didn't use 0 to 50. We might want to make this till 2 million or something along those lines. Because we didn't do the rounding this time when we put it in. So now,
Yeah, that's what I just asked too.
there we go. Do you need to see my window again?
No.
We definitely can see where those two are hitting, right? So what do you do?
Second trace.
Give second trace. Which one?
5.
Number 5. And let Blinky do his job. So Blinky says this actually happened during the table because it was about 40 years later, and it was 1,074,919 was about where those are hitting each other. So if our table started in 1950, and Blinky just told us it's going to happen about 40 years later, when did this supposedly happen? 1990. Kind of interesting to go on the computer and see whether or not that actually happened. But their two populations were supposed to be about the same, and that amount was 74,919. And again, we could put that into a sentence and say, in approximately 1990, they had the same population of 1,074,919. So sometimes I can only get through the first one of these with students, but I wanted to do the second one so that you could see. Yeah, we put the same kinds of numbers in there, but we didn't round the second time around. So when we hit graph, we get this really weird thing, and we need to say, okay, what did we do differently? How did this change? What was in the table? And think our way through that. So we do have another piece to this, but I better look and see the time. Ah, we're fine. All right. So now you can put the calculator aside. And remember, on the page right before this, it does have all of the buttons that you need to push and all of that good stuff. So hopefully if you get home tonight and you're thinking, well, I can't find this, I do want to remind you too, if you're saying, I don't have a graphing calculator, if you do not have an Apple iPhone, you can go to the Texas Instruments website and you can download a copy of the graphing calculator on your phone. It looks just like the graphing calculator. So that would give you good practice and it would actually give you something you can use for homework outside of class. And again, they have some in the library, but they're going to be a little bit older models. So where do we go from here? Well, sometimes our lines don't hit each other. And in the real world problems we were talking about, we keep hitting the window a little bit bigger so that we can try and see where they hit each other. But reality is not all lines hit each other. They don't. So we have names for what we like to see in math and what we don't like to see. First of all, the name consistent. In math, we love to be able to give an answer. We love to be able to say, it's right here. Here's the point where it is. So that's called consistent because it's consistent with what we like. We like to be able to say, here it is. What's inconsistent is no solution. We can't stand that. We don't like having to say, we can't find it. We can't tell you what it is. So consistent is we get an answer and everything's good like it should be. Inconsistent is when we have to write no solutions. And we can see down here, there is a no solutions answer for this one. Parallel lines are not going to hit each other. They're just not. So that's an inconsistent answer there because we'd like to say, hey, they're going to hit at this spot, but they're not. So a consistent system gives us at least one solution. Now, why do I say at least one solution? Because it is possible that we might have to say that the system has infinitely many solutions. That happens when one line graphs right over the top of the original line. And you guys are going to have to grab a pencil or a pen or something of different colors here because look what they did. We've got your black and white packets, and here it shows our red and blue, and yeah, they hit at one point. Yay, we can give them an answer. That's consistent. But red and blue together make purple, and that's why this one looks this way. So what really happened was they had a red line, and then they went to graph a blue line, and it went right over the top of it, and it made purple. Now, we do get to give an answer for that. We have to say that has infinitely many solutions, because if you think about it, those two lines right on top of each other, they're always intersecting. And lines go on forever. So it is going to be consistent. We will get to give an answer. So what's with this other stuff, this independent and dependent? Well, independent is when you're by yourself. So that means if we get one answer, if we can say, hey, these two are hitting each other at the ordered pair 4, 2, that's an independent solution. We got one answer. But this middle case right here, where we have to put infinitely many, that's called dependent. And that's because those lines actually ended up being the exact same line. So they depend on each other. So really, this is a very visual concept when you go through it. You think, okay, if I get an answer, that's good. That's called consistent. We like answers in math. If I see I'm not getting a solution, they're parallel lines, that's inconsistent. We don't like that. We don't like to say, hey, this doesn't have a solution. If it's 1 point, boom, hits, that's independent. There's one answer. But if it ends up being infinitely many because one line is over the top of another line, then we have to put dependent because the answers depend on one line going right on top of the other. So this is just a little vocab piece. We already did the tough stuff today. The tough stuff today was getting our graphic calculator to work the way we wanted it to work. But now it's, how are we going to know this when we see it? So this one says we're going to classify this system. We don't want to have to graph it. So I think, well, how am I supposed to know? How do we know when two lines are parallel? How do we know if two lines are parallel? Their slopes are the same. So if we take a look at the slope and we see the slopes are the same, we'll know we have no solution because it's going to be parallel. If they end up being the exact same line, then we have to put infinitely many solutions. And the best way to do that is just to solve for y. If we get y by itself, then we'll be able to give them their answer. So this one starts as 4y minus 2x equals 6. And we would add 2x to both sides. And we would divide by 4. So we get y equals 1/2 x plus 3/2. So now I'm looking for two things when I look to the next line. Maybe the next line has the same slope, but it has a different number behind it. Well, then I know they're parallel. And then I'm going to know it's inconsistent because it won't have an answer. But maybe the other line ends up exactly like this one. And then I know, oh, yep, that's consistent. We have to put infinitely many solutions, so that's going to be a dependent answer. But maybe they're two totally different lines. And if that's the case, then they're going to get one answer, so it'll be consistent. So let's look at this one. This one's a little easier to get y by itself. So we have y equals 1/2 x plus 3/2 and y equals 1/2 x minus 3/2. Are they the same line? No, super close though, right? Yeah, they were trying to make us think they were going to be the same line. Are they parallel? Yes. These slopes are exactly the same. Do two parallel lines ever hit each other? Nope. So this is inconsistent. We don't get to put an answer down. So we didn't have to graph it to know. All we had to do was look at the slope and the y-intercept, and then we can tell. So let's go down to the got it down here. It says, without graphing, are we looking at independent, dependent, or inconsistent? So what are we going to do again? Solve for y. All right, so top one. How do you solve for y? What are you doing? Because I can see a whole lot of you with your heads down. How are you doing? Add the 3x, exactly. All right, so there's the top line. The top line is 3x plus 4. Change colors and go after the bottom line. Ew, that doesn't look like a lot of fun. You want to deal with the fractions, or should we get rid of the fractions right away? Get rid of them? All right, let's multiply everything by 3. You don't have to. You could move the x over first and then multiply. Whatever you want to do. So now all we have to do is subtract 3x from both sides. And divide by -1. Now we need to figure out, are they parallel? Are they the exact same line? Well, I've got green and blue up here. Are they the exact same line? No. Are they parallel? So what do we put for an answer? Inconsistent, exactly. If they're parallel, they're inconsistent. let's look at the middle one. Ew, that looks like a lot of work. How are we gonna get y by itself? Then what? Divide by 3? Right, so there is the first equation. How do we get y by itself in the bottom one? Oh, I like that one. Are they the same line? Not even close, right? Are they parallel? No. So these are two very different lines. They're going to hit somewhere. So what do we put if it's going to hit somewhere? We didn't see this one yet. It is consistent. We're going to get an answer. Are we going to get one answer or infinitely many? Well, you told me they're not the same line. So how many answers are we going to get? Just the one. This is independent. So this one is consistent and independent. We're getting one answer. All right. I'm going to have to stop there. And I know some of you already went ahead and did C anyway. So in C, they end up being the same line, right? So consistent and dependent for that one. Well, there's 3-1 day 2. So we're still solving these graphically, and that was our objective, but today we're using that graphing calculator to find, especially some of them just have nasty numbers in the tables, so that makes it a little easier. But we have to remember all the buttons to push.